So, today we are going to look at how to establish a formula for finding the cardinality of the power set of a finite set. So, let us consider box n is nothing but set of numbers 1 to up to n, right. For example, you can take 3 is nothing but 1 2 3. So, basically we denote power set of 3 as the collection of all subsets of this set box 3. So, if you want to list it, it is very easy. We first find singleton subsets like this, then we club 2 element subsets. We have 2 3, we have 3 2. Now, we have finally the complete set is trivially a subset of that, and we have one more fellow which is the empty set. So, empty set is a set with nothing inside there, and that is trivially becomes the subset of any set, right. So, why you can think of this, and it is followed from the truth table of a proposition like P implies Q. So, you have to check whether when this statement is true, right, and when it is not, and then you will understand why phi is a subset of any set. Okay. So, now we just want to count it. So, if you count this, you have 1 2 3 4 5 6 7 8, you have 8 fellows. So, this 8 is okay. So, let us start from something trivial. For example, what is the power set of just one element? So, that this is set of all 1 and only you have phi. So, you get 2, right, the cardinality is 2. So, this implies the cardinality of the power set of having one element is going to be 2. So, there is something like a progress. So, I can write 2 raised to 1 here, and 8 can be written as 2 raised to 3, right. So, we have observed something like that. So, right. So, we assume whether is it true for all, and I mean is it true for our subset. Like if I assert like this, then we do not know that when we try to prove it. So, how do we try to prove this? There are many attempts we can do. For example, I will give you some possible bijections that you can do. So, one of them is, right, if you look at the the strings of length n using zeros and ones, then you will get some idea, and otherwise you can count this. We choose first singleton set, then we have to choose 2 element subset. These numbers are actually corresponding. Then finally we get and choose n, and we also choose empty set. So, we actually have this also. So, you can prove this is using induction or something, then that will actually give you one idea of proving that. But now I am going to attempt something different. I want to use indicator function and some other ideas to prove this, right. So I define an object like this, and before that I just want to introduce a set B, which is all functions from box n to the set 0 1. Okay. So how many functions of such form? It is very easy because right, I mean so 1 has 2 possibilities, 2 has 2 possibilities because either 0 1, and finally you have n has 2 possibilities. So then combining these ideas, then how many functions it is having? So it is 2 times 2 times up to 2 n times, so that will be 2 raised to n functions possible, right. Okay. So yeah, so number of functions from a finite set to a 0 1 set is just 2 raised to n. So that is my set B, right. Okay. Now what is my idea is, I want to construct a bijection phi from the power set of box n to B, then it is a bijective proof of, because if I count, if I able to establish a bijection, then the cardinality of B is equal to the cardinality of the power set of n, which is exactly 2 raised to n. So how do I do that? So that is my idea. So I believe that this is an easy task for you to understand. The number of functions from finite set to 0 1 set is just 2 raised to n, because every element in the domain has 2 possibilities. So if you take using multiplication rule, you will get 2 raised to n. And now I want to establish a bijection. So before that, I want to define a function A, which is subset of box n. So let it be like that. Then corresponding to this A, I define a function which is chi A or something like that from to 0 1. So the function is defined like this. Chi A is equal to, I mean you have to chi of x equal to 1 if x belongs to A, 0 otherwise, that means x does not belongs to A. So now the idea is, this function is actually belongs to B for every A subset of n, right. So this gives me a construction of a bijection that I have desire for, because I can define like this: phi is from the power set of n to B like this. Each set is from the power set of n, that each subset is goes to a function chi A, because you can see that chi A is belongs to 0 1. So my target set is fine. Now the only task is to prove the bijection. So I have to first prove it is injective, right. So how do I prove that it is injective? So I assume phi of A is equal to some phi of D, right, 2 subsets, and this implies chi A equal to chi B, chi D. So what does exactly mean? So that means chi of A x equal to 1 if and only if chi of d of x equal to 1. That these are functions on box n which takes elements to 1 or 0. So, what is the meaning of this? So, that means the set A is equal to D, because otherwise they will not be equal, because right. So, when the element is available in that particular set A, it gives 1. So, similarly that means the same element is available in D also, otherwise it is 0. So, that is not so that then what we have proved is phi of A equal to phi of D implies A equal to D, that means it is injective, right. Now, I have to prove the surjectiveness, or what we can call the ontoness. So, ontoness means I have to take a function f from B and I have to produce a subset. I have to produce a subset of n such that subset, let us call it some subset, we can denote it by some k, actually gives you this function f, right. So, that is what I need. So, how do we do that? So, since f is belongs to B, f is a function from box n to 0 1, and suddenly I could construct the pre-images of 1, right. So, for example, f inverse of 1, similarly I will denote it as 1 raised to minus 1. So, this is a subset of box n. Now, let us check whether this will work or not, right. So, this subset will, where this subset will map to B. So, for that what is the function? So, phi of 1 inverse is equal to and what is our function, which is k of k, right. So, chi of 1 inverse. So, the thing is, it is enough to prove that f of k of 1 inverse of x equal to 1, and if and only if f of x equal to 1. So, that is the thing I have to prove, right. Then we can see that the both functions are equal, because they are from 0 to 1, right. They are yeah. So, right. So, how do we prove this is? So, what do you mean by this chi of 1 inverse of x equal to 1? What is the meaning of this? This means the x is belongs to 1 inverse, right. So, that means f of x equal to 1, that is the definition, right. X belongs to pre-image set of 1 means f of x is equal to 1. So, this is an equivalent case, and if f of x equal to 1, you can prove this also true. So, that means, and similarly you can prove when x equal to 0, then that is also we can prove easily. So, if at all one element is if at all we have one inverse is non-empty, this is true. But there is a case when one inverse is empty, right, because what is the meaning of this? That means where phi maps to, which function phi maps to. let it be called f bar. So, this f bar is nothing but the function all the elements in the box n maps to 0, because if they all maps to 0, that means that is a phi set. So, except this f bar we have got the bijection, and for particularly in for f bar we got phi as a corresponding fellow. So, in that way we have found this function is onto. That means, I have established a bijection between p of n and b. So, the cardinality must be equal. So, that is equal to 2 raised to n. So, in this way I established this proof. Okay, so I think you have understood that, and you can go through it anyway.